everyone. Thank you for joining us. It's a great pleasure to have Dr. Lorenzo D'Amico today with us. Lorenzo holds a master's degree in biomedical engineering and PhD in nanotechnology from University of Trieste. And he has worked widely with the CMF beamline at the Electra over the last few years, and also with the team at the IMBL. And since March, he has joined the Impact Group. So thanks, Lorenzo, for accepting to do this presentation. And over to you. The title of you can probably mention what the topic is. It's Novel Multimodal Approach for Lung Fibrosis Characterization.
Yes. So can everyone see my screen and also hear me?
Yeah.
So good morning or good afternoon or like good evening, depending on which part of the world are you following this talk. So today we'll present you this novel multimodal approach for lung fibrosis characterization. This was my PhD project. And today, let's say my aim is to convince you that, most of the time we are used to say less is more, but in this case, I will try to convince you on the contrary. So if we use more stuff, actually it's better. So, okay, it's not working. So a bit of the outline of this talk. So there is a brief introduction and motivation and the objectives, why we decide to develop such a multi-pipeline and why we choose lungs as organ, the material and method, so all the technique that we apply during this 3 years of the PhD, and then of course the results. So the first things is we start with lungs. We decided to go for lungs because these are the most important organs in our respiratory system. And also lungs have some particular features, such as a very high surface for the gas exchange. And then and thanks for their composition, they have specific mechanical properties, such as the compliance. So this elasticity that allows them to expand and contract, allowing us to breathe. The problem, though, is that there is also this pathology that is called fibrosis. And fibrosis is basically this pathological bundling process in which the healthy tissue, so that so-called parenchymal tissue, is replaced with connective tissue. Connective tissue is basically this huge group of fibers. And we have different types of fibers in our body, such as collagen, elastin, and fibrin. So the lungs can undergo to this pathology, and this is basically what happens. So if we have a normal lung should look like this. These are like the alveoli, so basically the end part of the branches inside the lungs. And the problem is that if there is an exposition to, for instance, air pollution, chemicals, or radiation, this triggers lung fibrosis. So in this case, we have this deposition of collagen fibers. These that I just mentioned are just few of the well-known causes of fibrosis, but in most of the cases, we actually don't know what's going on and why the fibrosis is triggered. In this case, then the type of fibrosis is labeled as idiopathic. So every time that you hear the word idiopathic means that actually we don't know actually what triggers the disease. The important things is to bear in mind is that we have a normal lung, and due to fibrosis, we have the formation of scar tissue and also remodeling of the tissue, such in this case. So again, this should be the end part of the branches where we have the alveoli. And as you can see from the picture, maybe laser. I hope you see like the laser. So here we have the bronchi, and you see that in this part of the alveoli, like there is a distortion that here are how they should look like when they are healthy, but here is all distorted. And also we have this kind of scar tissue between like the branches. Then the other important things is fibrosis changes the mechanical properties, because as everything in nature, the mechanical properties are linked to the composition of our material or media. And in this case, the lung has its own composition, but when we start to put fibers on it, we change the composition, and thus it loses its compliance. So it becomes stiffer and it cannot expand and contract as it would do in its homeostatic condition. Homeostatic condition means when it's healthy. Saying so, there are several motivations why it's very important to study lung fibrosis. First of all, lung fibrosis is a very severe and progressive lung disease that so far has no treatment option. Then we all know that during the period between 2019, 2020, we all got stuck at home due to COVID-19 pandemic. And it has been forecasted that the number of lung disease will increase during time after this pandemic. So it makes a lot of sense to start studying them now. The other problem is that, as I mentioned at the beginning, like lung fibrosis is a pretty general disease. So we know that there is this deposition of fibers, but nothing more. And so far it's just considered as a just big and general disease. And mostly because all the pathomechanisms leading to lung fibrosis are largely unknown. So saying so, these are some motivation why we decide to go for this particular disease. And the assumption that we made starting this project are maybe there are different causes creating different subtypes of pulmonary fibrosis. And this could help us because if we know what induces lung fibrosis, then we can develop a treatment. But before going to the treatment phase, we have first to characterize them. So the idea is to, as I mentioned at the beginning, I want to convince you that maybe using more than one technique is better. And so we developed this multi-technique pipeline that has to be thought as some tiny pieces of a puzzle that you can put all together to have a broader view on the problem. The aim of this pipeline is to the identification of fibrosis subtypes. And then at the end, also, there should be a phase of optimization that has not been performed yet. So the optimization phase means that in science, we know that we have to prepare the sample, run the experiment, collect the data, analyze. If we then multiply this process for 5, 6 techniques, of course, you agree with me that the number of days or months that we need to analyze the data increase dramatically. But would be super interesting also to kind of trim this pipeline. So like get rid of the maybe redundant technique and still get that maybe provide roughly the same results as the others. So shrink a bit the pipeline, reduce the number of technique, but still get good results. Unfortunately, this optimization phase has not been performed yet, but is in my to-do list for the future. So saying so, there were, of course, some challenges because, of course, when you start using more than one technique, you have to keep in mind that the sample preparation may be very tricky because we know basically that a good sample preparation, I would say, is already 95% of an experiment. The problem is that when you start to use different technique, of course, like in literature, we can find a lot of sample preparation that I'm Italian, so I would make like this comparison. So kind of like recipe to prepare like your sample. And for instance, if we want to scan something with computed tomography, in most of the cases to highlight some features inside our sample, we need to use contrast agents. If you want to perform, for instance, histology for who is not in the field, basically is the thin sectioning of a sample that has been before fixed and embedded in a stiff matrix such as paraffin. And then this sample is this thin section of sample is colored, so with some special dyes to highlight the anatomy of the sample. Here, the sample preparation required the embedding, for instance. Or if we want to characterize, for instance, the mechanical properties of the organ, the best thing would be to have the organ fresh or frozen. You start to understand that if we like take into account like this second column, you start to see that all these 3 techniques already require pretty different sample preparation. And therefore, if we apply the recipe as it is, of course, this would create a really big mess because, of course, they are pretty incompatible. Then the second big challenge was due to the disease itself. So when we speak about fibrosis, fibrosis is pretty inhomogeneous inside our organ. So for instance, here, this is an image of an histology for a lung. And inside the same lung, we can find some region in which actually we have fibrosis and also some region in which the tissue is pretty healthy. So if you want to study the tissue, the same tissue with more than one technique, of course, we need to know where we are measuring. Otherwise, we could end up measuring with one technique, one fibrotic region, while with the other one, maybe an healthy region. And of course, like the outcome of the results would be pretty different. In particular, inside the lungs, there are, I would say, three major important sites, which are the parenchyma, so the healthy tissue, the consolidation tissue, so where actually fibrosis happen, and also the perivascular region, where we have the collagen deposition. And in particular, this is very important due to fibrosis because, as I mentioned already, we have this fiber deposition. Of course, here we are speaking about multi-technique, and it's pretty unlikely that all the techniques are all in one place. So actually, this PhD students was carried out half part in Italy at Elettra, in Italian synchrotron, where I performed 2 out of 4 technique, which is phase contrast, micro-CT, and infrared spectroscopy, while the second part was carried out in Germany, in the University of Göttingen and at the Max Planck Institute, where I performed the histology and the atomic force microscopy measurement. So what is the aim? The aim is, at the end of the day, to characterize lung fibrosis in patients, in human. The problem is that most of the cases, like the starting point and the aim, are slightly shift, because in this case, it's very tricky to start such a study with patient materials, because in most of the cases, like a patient passed out due to more than one disease, and this is the so-called comorbidity. So if I'd start with patient materials, first I should screen and understand if actually that patient died just to lung fibrosis, and then I could start doing the measurement. So instead of complicating my life, we decide to go with an animal model as a starting point. So the animal model, they have several advantages over like patient materials. First of all, also patient materials is pretty rare, and so it's pretty precious. So I didn't have the access to so many materials at the beginning. While like animal model, we can purchase mice, and so it's easier to get it. But besides saying so, there are several motivations why you should use animal models for such studies. So first of all, it's easier to control the environment, so we have less variability between the experimental group. There is the possibility sometimes to apply genetical alteration to the mice, so we tailor basically the animal model to then suit perfectly our scientific question. And then in particular, in my case, we found out from the literature that there was the possibility for the induction of lung fibrosis in different way. And this was actually a key aspect of using these animal models, because knowing since the beginning that the induction of fibrosis was made in 2 different ways, of course, could help me to understand if actually I see difference, then I could let's say, explain that the difference are due to the difference induction. Otherwise, if I don't see difference, of course, I can also state that actually, okay, there are 2 different ways of induction. I don't see difference, then this means that lung fibrosis doesn't depend of the induction. So lung fibrosis is just one big disease. So in this experiment, in this pipeline, we use different mice model. The first one that we will call genetically modified. This is a genetically modified knockout model that was developed in Germany, in which basically they delete one ubiquitin ligase. And basically this then triggers the formation of scar tissue inside the lungs. I'm not a biologist, but if you are interested in more details about how they develop and how this model works, here you can find like the reference. Then the other model that we use is a very well and established in the literature, that is the bleomycin-induced model, in which we basically induce fibrosis by the injection of this bleomycin through the trachea. This reaches the lungs and then triggers the formation and deposition of scar tissue, which is one feature of fibrosis. Then we also tried this treatment that is called nintedanib. Nintedanib is not a treatment meant to solve the problem of fibrosis, but rather to slow down the process of development. And then, of course, we use some controls. So for each mice, before going on, like just a bit of context and what is the state of the art. So how we treat fibrosis. The gold standard for fibrosis quantification is in medicine is histologies. And histologies allow us to assess the severity of fibrosis by means the so-called modified Ashcroft scores. This is a score in which basically several people have a look at the histological image and then scores a value between 0 and 8, where 0 means that there is no pathology, 8, there is a very severe fibrosis. And this allows us to assess the severity, but actually doesn't tell us anything about what triggers the disease itself. So, for instance, here we can see like this lung, and this lung actually is not real. This is a dummy lung that I create taking one lobe from one model and one lobe from the other. And actually, if you are not trained or if it's the first time that you see such a pathology, maybe for you it's very tricky to distinguish which lung belongs to which group. And this is because I made on purpose this dummy lung using two lobes that belongs to two lungs that have the same Ashcroft score. So from a point of view of the severity, they have the same severity. So it's very tricky to tell why and how was the fibrosis trigger. So just for to explain you, like the left one is the genetically modified one, while the right one is the bleomycin induced. And this was just to give you like a take-home message that so far, like the established method do not allow for the discrimination of the models. And this is why we need actually more techniques for the quantification. Coming back to what we did, so this was our mice, then we induced fibrosis and we in vivo micro CT scanned the mice. And basically, this is what we get. At the beginning, before the process, the mice was healthy. And then after a certain amount of week, the fibrosis start to develop. And then these are basically two planar radiography that we took from the mice and to assess and follow up the development of the disease. What we did at a certain point when we were satisfied with the development, we sacrificed the mice, the lung were harvested, then were fixed and embedded into paraffin. So the samples that we use are paraffin block. The idea is to use paraffin block because paraffin block is the way that the worldwide hospitalization uses to preserve human materials in the hospital. So we have plenty of materials that can be studied with this pipeline. So the idea is that to prove that it's working on an animal model and then move right away towards patients because we have plenty of materials waiting for us in the hospital. So now we speak a bit about the technique. So the first technique that I will introduce you is the so-called phase contrast micro CT. This was carried out at the CIRMAP beamline of Elettra. So just to give you a bit of context and how does it work and how it differs from what we are used in the clinic. So in the clinic, we are used to imaging samples based on this absorption modality, in which basically it's like taking a picture. So we know that we have basically the negative of our sample. So what happens is that we have the X-ray source. The X-ray source produces some X-rays that they are absorbed from the object. And then we have a detector. The detector collects the X-rays. And thanks to this, we basically get an image. So what happens is basically that when the sample when the X-ray impinges on the sample, it got absorbed and then basically it reduces its amplitude. And thanks to this reduction in the amplitude, which is an absorption, then we get what we are used to as an image. So for instance, here we have an image of the bone. So the bone absorbs the photons and then we can see basically the image. But this works well when we have materials that absorb a lot. And when we speak about clinical routine, in most of the cases, like we have organs that are basically 99% composed by water, and water is basically transparent for X-rays. And so this modality doesn't work that well. The other things that we can use is this so-called phase contrast micro CT. phase contrast micro-CT in the setup differs a bit from the absorption image, because you see that here the object is pretty close to our image detector, while here we basically have the object that is a bit far from our image detector. So what happens here is basically, as I mentioned, the X-rays passes through our object. In particular, if our object is transparent, we don't see and we don't appreciate any changes in the amplitude. But what we see is that some rays are refracted. And if we give enough space to them to interfere, they create these interference patterns. And if we have an image detector that is as a resolution enough to resolve these patterns, then we can create an image. In a nutshell, what happens here inside the object is that all the X-rays that pass through, basically they are kind of delayed. And so you can start seeing that here first the peak matches this peak, but after it passes through the object, this peak is not matching this one. And this phi is basically this kind of phase shift that allows the X-rays to interact in destructive or constructive way and creates this pattern. So just to prove you the potential of and the power of this technique, here there is a lung. Here up is reconstructed with using the absorption modality. And basically, you cannot appreciate that well its structure. While here, using the phase contrast image, you can see that you start to appreciate, like, this one is a bronchial, and here you start to see also the parenchyma. And the other nice things is that in this case, also, we can reduce a lot the dose that we give to our sample. In this case, I was not that interested in the dose because I was scanning paraffin block, but for a future application, for instance, some patients, this is a very crucial feature. But beside very nice images, what does phase contrast micro-CT give us? So it's a non-destructive technique because I can image my sample without destroying it. Give us 3D information, as you can appreciate here from this image. So this is a 3D reconstruction of a lung that was embedded into paraffin, and also provide us morphological information. So here in the top left corner, you see this is a cube that actually I extracted from a 3D volume. And thanks to this, we can extract some features such as the percentage of tissue that we have. Of course, the higher the percentage of tissue, the likely is that that lung is fibrotic. Then the other important things is that thanks to phase contrast micro-CT, we can scan the paraffin block, and actually we can provide the position of the fibrotic region inside the paraffin block. Because what usually is done in the clinical routine, they take the paraffin block, they trim a bit, and then they start cutting. They perform some histology on those slices, then they cut even further, they extract other slices, but this cutting is basically performed in a blind manner. And for pathologies like fibrosis, this is a problem because, of course, since fibrosis is not homogeneous, if we are unlucky, basically cutting, we might cut out all the regions that are fibrotic and just stay in the region that are healthy. While in this case, we can precisely measure the distance from the surface of the paraffin block to the region where I know that there is a fibrotic site. And then I can just tell the technician, please, can you cut 2 millimeters after you reach the surface of the paraffin block? And then I can nicely extract the region that is inside this square. And this, it's called, for us, we name it like guided sectioning. A bit of results from this technique. So from this technique, as I mentioned, we can collect morphological information. In particular, here, I want to show you some information concerning the percentage of tissue. So what I did, I extract some cubes from the different volumes, and then I measure the amount, the percentage of tissue against the, so the percentage of tissue, so the number of pixels that actually were tissue against the total volume of my cube. As you can see here from the first results, we see that there are differences between each fibrotic model and their control. There is no difference between the two healthy control, and this was nice because, of course, why should I have difference in healthy mice? And also shows that there is no bias in the data. So both the control group were basically the same. But what was interesting is that there is no statistical significant difference between the two fibrotic models. Since phase contrast micro-CT was the first technique of the pipeline, I didn't have any other information at that time. And so the answer to this question, why there is no difference, at that time were actually two. Either phase contrast micro-CT is not enough. So with just this morphological analysis, I cannot provide information about like difference between the two fibrosis, or on the other hand, maybe fibrosis is just one big disease. So it makes no sense that between two different way of induction, I have differences. But since it was the first technique out of 4, there was still plenty of room to add new information. After this, I performed what I explained you before, so this guided sectioning. So from having the paraffin block, basically this is the surface. From the surface, I calculate this depth, and then I extract one slice of 5 micron that I use for histology, and then one subsequent slice of also 5 microns that I use for other techniques that I will explain you and introduce in a sec. Right now, we will focus on histology. Histology was carried out in Germany at the Max Planck Institute. And here in this image, you can see different staining, so different color palette. And this is due to the fact that I use different staining during my PhD. And this was because I did a bit of try and errors, trying to detect which one was the best staining for my scientific problem. So I started here with A, with the classic way of staining that is called hematocylin eosin. Hematocylin eosin allowed me to discriminate the fibrotic region, but didn't tell me anything else about, for instance, the fiber content. So from the hematocylin eosin, I moved to a staining that is called mastron trichrome that is meant to stain connective tissue, in particular collagen. And here I hope you can appreciate, but there is this blue region, and this blue region is collagen. The problem is that mastron trichrome is just a general staining that stains collagen in general, but in our body, we have more than 100 types of collagen. So just knowing that in that position there was collagen was not enough, since my speculation is that different causes might lead to different fibrotic types, so maybe different type or different amount of fibers. So we decide to move and to, let's say, upgrade this connective tissue staining using the so-called picoserious thread staining. This is also a staining for connective tissue, but as is a disadvantage, advantage that if we image the slice with a filter that polarizes the light, this allows us to discriminate the type of fibers, in particular collagen 1, that here is displayed in yellow, or collagen 3, that is displayed more in green, inside our lung. So after this try and error, I decided to go on with the picoserious thread. That was the type of staining that I select for my study. So this technique allows for to discriminate and detect the deposition region, so where we have fibrosis. Can we use as a reference map because fibrosis, because the lung could be imaged entirely. And also, thanks to this polarization filter, we can get insights on the type of fibers. In this case, I also run this Ashgrove score measurement to detect the severity of fibrosis. Also, as I would say, a double check to see if actually between the two models there was a difference in the severity. Actually, in this case, there was not. So the two models could be compare each other. After histology, as I show in the previous slides, we also collect a subsequent slide of 5 microns. On this slice, we perform the so-called infrared spectroscopy. Infrared spectroscopy was carried out in Italy at the CC Bimlen. And infrared spectroscopy is a very nice technique that provides the fingerprints of the elements that we have inside our sample. So how does it work? So the infrared light impinges on the sample, and then this triggers vibrational vibration on the molecules that can vibrate in different way, either stretching, bending, or rotating. This way of excitation basically creates this so-called spectra, and each spectrum, and each peak of the spectra correspond to a chemical bound. So in this case, basically we have a kind of barcode of all the elements that are inside our tissue. And it has been demonstrated in the literature that if we collect the data in this particular windows of our spectrum, we can discriminate between different type of collagen. So I decided to use this technique to discriminate the type of collagen that I had inside my sample. So, sorry. Okay. So I don't know what happened. Sorry. Okay, so what I did, I basically started with pure collagen 1 and pure collagen 3. These two protein can be purchased, and I prepare them as solutions. I measure them, and then I also measure my samples. What I did then on the spectra collected on my samples, I ran this unsupervised machine learning algorithm called k-means clustering, in which basically I create two clusters, one of collagen 1 and one of collagen 3. And then I assign as centroids of this cluster the pure collagen 1 and collagen 3 signal. And then the algorithm basically was checking the spectra of each pixel and comparing to the collagen 1 or collagen 3 spectra. And if the spectra was closer to collagen 1, then the pixel was labeled as collagen 1. Otherwise, if it were like more close to collagen 3, this was labeled as collagen 3. And I tried to use the same color as in the PQ series red staining. As you can appreciate here, in A, we have an example of a fibrotic lung, while in B, we have an healthy control. And as you can see already visually that there is a difference in the amount of collagen 1 that is more predominant in the fibrotic one, while in the healthy one, there is a predominance of collagen 3. What I also did for validation, I took the same exact spot in the polarized histology to also check that my results from the infrared spectroscopy k-means clustering were consistent. And as you can see also here, we have a predominance of collagen 1 samples, pixels. And then also to show that there was a consistency between what I found between the infrared spectroscopy data and the polarized histology, I overlap the data using this checkboard visualization. So these two techniques can be put together, and what we can get putting together them is that with the histology, we can validate the infrared spectroscopy results, and then from the infrared spectroscopy results, we can quantify the number of collagen 1 or collagen 3 pixel, and so also, for instance, calculate a possible ratio. Indeed, in most of the respiratory disease, there is a change in the ratio between collagen 1 and collagen 3, and this may be helpful for its detection. Then the last technique that I use is the so-called atomic force microscopy. Atomic force microscopy was used on the same thin slice of tissue, which I measure with the infrared spectroscopy. This is a technique that can provide us the biomechanical property of the tissue. So as I mentioned at the beginning, this is a key feature of fibrosis because we have fiber deposition that change the composition and thus the elasticity of our lungs. So how does it work? We have basically a cantilever that approach our sample, and then we have this plot in which at a certain point the plot start to go up. And if we fit basically the steepness of this part that goes up, we can retrieve the so-called Young's modulus, that is a parameter to measure the stiffness. What I did, so I selected different region inside the sample. In particular, I selected the same region that I also measure with the infrared spectroscopy. And here are divided in perivascular regions, so the region around the blood vessel or the bronchial, where I have collagen deposition, the parenchyma, and then consolidation regions that, of course, were just present in the two fibrotic model. And as you can see here, there are pretty nice difference between the two models and also the controls. The only things is that so far, all the techniques but the AFM were imaging technique. So the AFM actually gave me just one number. And to represent this number, so the stiffness, we decide to represent it as bars. So the higher the bars, the higher the Young modulus, and thus the higher the tissue. But so far, I present you a lot of technique, but would be super nice to have all this information displayed in one big image. And actually, we can do it, but there is a problem. So when we start cutting the paraffin block, we introduce some deformation due to the blade that we use to cut the paraffin block. And so this deformation needs to be corrected. And so we have to perform the so-called elastic registration. If there were no deformation, we could just perform a rigid transformation. But in this case, we have also to account in non-linear deformation due to the cutting blade. So how does it work? In a nutshell, we have a reference image, so an image in which our sample was not deformed, a floating image in which actually our sample is deformed. We apply some transformation to modify the image. We have to interpolate the image because, of course, our image is not as the original one. With some metrics, we basically check the reference image with the floating image after all the transformation. And if all this part here was optimal, so the difference between the two images is basically zero, then we can merge them. Otherwise, there are some optimizer, and so we have to change a bit the transformation and rerun all the process until the floating image is transformed in an optimal way, and so we can register the two images. This is basically the output. As you can see, there is a RGB image, which is our histology, and this grayscale image that is the micro-CT slice. And here, this basically black part are the deformation that were applied on the histology in order to compensate this elastic deformation that happened during the extraction of the slice. Maybe this image is a bit small, but if we zoom in particular in these two regions, you can definitely appreciate that this elastic this elastic registration worked. And for instance, here you can see that there is a pretty nice continuity between like the tissue as well here. And so this shows that the elastic registration was performed in a very great way. Here, of course, this was just the first step. So when I registered the histology on the micro-CT data, while here there are also the further step that I performed to elastic register all the other technique in the environment of the micro-CT data. So just to show you what is the output, here there is the paraffin block that was scanned with the micro-CT. From the paraffin block, we can, of course, remove the paraffin and we can get just the lung. We can actually go inside the lung and show the histology that is perfectly aligned. Here, there is a cube that I use to extract the matrix of morphology. Here, there is like the collagen of the collagen 1 and 3 from the polarized light. This is the infrared spectroscopy, and as usual, this video stops when I'm sharing the screen, sorry. So I don't know why. Okay, and also here we have the AFM data. I'm sorry, but sometimes when I'm sharing the PowerPoint, the video gets stuck. And also here there are the AFM data that are precisely registered. And so now basically we have all this information in one big image. So a bit the results, we were capable of develop a multi-technique pipeline in which basically we started from a paraffin block, and then we got different information from the propagation-based images, micro-CT, histology, infrared spectroscopy, and AFM. And here, basically, there is the big picture of all this data gathered together. We achieved the analysis of the same region of lung with more than one technique. Here there is the histology, and here there is, for instance, the atomic force microscopy region that I measure. And as you can appreciate, even if it's slightly 5 microns above, below, the architecture of the tissue is basically the same. And then last but not least, we were also capable of finding difference between the fibrotic models. Here on the top right, you see this big matrix. This big matrix is called a dendrogram. A dendrogram is a clustering method that is used to compare basically results that are in more than one dimension. So the idea is that each row represents a sample. In this case, each row represents a mice, and each column represents a matrix. So in this case, we have 9 columns, and the 9 columns are basically all the data and the information that I collect from each single technique of the pipeline. At the beginning of this clustering method, each mice or each row is considered as a single element. And in this case, since we have 9 columns, this should be like a vector in 9-dimensional space. That, of course, I think is very difficult to imagine and also to display on a PowerPoint. So if we do it in 2D, I think it's way easier. So here we have this P0 until P6 that in this case would represent the mice. And then we can run this clustering method in which it exploits some similarity metrics and check basically each point with all the other points and see which one are the most similar. So when we start, these are similar and they are gathered in one cluster. And so we have 5 points, so 5 clusters. Then after this, we have 3 clusters. Then we would have 2 clusters, and then at the end, it will also gather this one. The idea is that we can also stop this iteration process. For instance, if we stop right here, and in this case, if we stop right here, we can see that basically we have 1, 2, and 3. So 3 clusters that actually are 1. These are, sorry, maybe let's see. Here are the controls, and this yellow one is a bleomycin-induced mice, in which we also use the nintedanib treatment. The red one are the bleomycin-induced fibrotic mice, and the blue one are the genetically modified one. There is an outlier here, so this bleomycin-induced was clustered as a genetically modified one, but yeah, we know that in science, when we get 100%, maybe something is wrong. But also here, in this case, we also got that one fibrotic mice that was treated ended up with actually just fibrotic. So in this case, I actually check why this happened. And if we look, for instance, at the metric of the percentage of tissue, you can appreciate that in this case, in the blue one, so the mice that was clustered with the healthy one shows a pretty homogeneous tissue. That is what we would expect from healthy mice. And also the standard deviation is pretty homogeneous. While here in this case, we see that the percentage of tissue varies and changes a lot, and also the standard deviation is pretty big. So in this case, also this shows that this pipeline is capable also to provide information on possible follow-up for treatments. And of course, this was not just me, but I had a lot of support from the left, my group in Italy, my cat that support me all the way through my PhD, and also like my group during my experience in Germany. Thank you so much for the attention.
Thank you so much, Lorenzo. That was a brilliant presentation. Let's open the virtual floor for questions. Can I start by asking for your elastic registration? You mentioned you had different reference. Wasn't CT always the reference for?
So basically what I did is, so from the CT, I have an image that has slightly the same size of the histology, so it was easy to register them. Then the other techniques, of course, I could not have, let's say, a dimension that was big as the histology. And basically what I did, I used the deformed histology to then, so in which the elastic registration was already compensated, to then register the ROI or small technique. So every time, basically, I was doing this chain approach in which I was register one image, so it was non-deformed, and then using the non-deformed to as a fixed image for the next technique. Also, the most important things is that to find the same region, I use like Photoshop in most of the cases to crop, and with the CT at a certain point zooming in, I had very bad resolution, while for the histology, since I use a very nice microscope, I could zoom in and I still got a very nice resolution.
Thank you. Any questions for Lorenzo or comments? And how many samples do you had in total?
So I had, I can show you again. I don't remember on the top of my head, but so 3, 6, 15, 16. Actually, I had more, but during the process, sometimes, for instance, for the AFM, I had to remove the paraffin, and sometimes if the slice were not attached perfectly to the slice, removing the paraffin actually also deattached the samples. So during the process, I also lost some samples. Some of them, they were not that nice because of the embedding. So yeah, I started actually with something around 30, but then during the process, some of them, like some data were not useful.
Yeah. Yeah, well done. We have a few minutes more if there are questions. Otherwise, can probably conclude this meeting. Magdalene, do we have any presentation scheduled for next month?
I'm still looking for presenter.
Okay, sure. So Magdalene will update us when that's scheduled. Thank you everyone for joining us today, and thanks again to Lorenzo, and very well done. See you soon.
Thank you.
Bye.
Bye.